Okay, so let me make some comments.
Sir, so
And the most important comment.
homogeneity of space is related to the second order partial derivative with respect to x, মানে del x স্কয়ার এর ওটার সাথে রিলেটেড নাকি মানে এরকম?
It is related if the equation is not a matrix equation, because you will see that not in this course, but in the future, you will see that the Dirac equation, which describes the electron, is first order in both space and time. And of course, it is also, consistent with the homogeneity of space. And the Klein-Gordon equation, which is a quantum field theoretic equation, is second order both in space and time. And that is also, is also considered with the homogeneity of space and time. So the answer to your question is that the first order in space is allowed as long as the equation is a matrix equation. But the Schrodinger equation is not a matrix equation. Okay?
Okay, sir.
Yeah, that's a very good question. Yeah. So the most important comment is that, and all of these, wonderful properties are allowed, is that the Schrodinger equation in its time-dependent form is a complex equation. Okay. So this is the first time in the human history, that complex numbers become essential to the description of nature. You can do classical physics with complex numbers, but you don't have to. Engineers use complex numbers for electrical engineers use complex numbers for, signal processing and all that, because it's very convenient, but they don't have to. Those are just, good tools. They are not essential ingredients of the nature of reality for them. But for theoretical physicists, for the quantum physicists, complex numbers are an essential part of reality. And the fact that, the Schrodinger equation is homogeneous and isotropic, isotropic has to do with the fact that it is a complex equation. The wave functions. By the way, this psi is called a wave function. So the wave function in general is a complex quantity. Okay? So that's comment number one. Number two is that, so Schrodinger equation is non-relativistic, okay? Therefore, it cannot describe light, photon, for example. Yes, photon is by definition a relativistic particle, because it travels at the speed of light. Okay. Schrodinger actually discovered a relativistic equation, but it wouldn't work. And later in the course, we will see, we will come across this equation, and we will show you why it doesn't work. Okay. It's a non-relativistic equation. And why is it non-relativistic? Because it's first order in time and second order in space. And we know that for anything to be relativistic, at least it has to be time and space have to enter on equal footing, right? They both have to have the same order. Otherwise, a Lorentz transformation Lorentz transformation mixes up time and space, and therefore Lorentz transformation will not leave the equation invariant. Okay, so very importantly, Maxwell's equations are also first order both in time and space, and that's why Maxwell's equations have the chance of being relativistic. In fact, Maxwell's equations are the equations that they are the object that inspired Einstein to come up with special relativity. Okay. The comment number 3 is that it's a Schrodinger equation is a linear equation. It's a linear equation, meaning that it doesn't have psi squared or psi cubed. So if psi 1 and psi 2 are solutions, then their linear combination, where C1 and C2 are complex numbers, is also a solution. And that's really why we can do Fourier analysis and stuff like that. They become so important. And the final comment that I have to make is that superficially, the Schrodinger equation looks like a heat equation. So a heat equation is an equation which is first order in time and second order in space, and it describes how heat propagates through a material. But heat equations are not time reversible. Because if they were time reversible, it would, violate the second law of thermodynamics or something, right? Then, we could have heat sort of, instead of dissipating, spreading out, heat energy would gather and become concentrated in one place. In other words, T going to minus T is not a symmetry of heat equations. But for Schrodinger equation, but you see, on a microscopic world, suppose you're looking at the interaction of, say, so suppose you have an electron coming in and a photon coming in, and then you can have an electron going out, a photon going out. So now if you run the time backward, what you will see is that you just see the same thing, but going in the opposite direction, right? You just see this. Actually, it's a little bit more subtle. It turns out that the time reversal of this process changes the charges of the objects. And because a photon is uncharged, it doesn't change its charge. So time reversal, so this goes time in one direction and this other one goes. So time reversal actually changes the charge of the particle. So, but since, we know that particles and antiparticles exist, both of these, these are both physical processes, right? So in the real world, this also happens in the forward time direction. So, this is my long-winded way of saying that, microscopic physics is time reversible. With charge conjugation. And it turns out that Schrodinger equation, because it's complex, is also time reversible. So if I do the complex conjugate of, if I do the time reversal of, Schrodinger equation, then what I do is that the first term changes its sign. Nothing else changes its sign. Nothing else. Of course, the psi dependence goes to psi minus t dependence. But this is not a Schrodinger equation. But now if I do complex conjugation of this equation, then the I becomes minus I, so I get I h bar d of psi star d of t minus h squared by 2m del squared psi star plus v of psi star. But this is the Schrodinger equation with psi replaced by psi star. So if psi is a solution, then so is psi star. And one can show that if you have a charged particle, that for charged particles, psi star describes the charge conjugate. So the fact that the Schrodinger equation is a complex equation also means that despite of it being of the same form as a heat equation, it's actually time reversible. Okay, so this is all I have to say, but I'm sure you guys have a lot of questions. So please shoot.
So if you take the conjugate of an electron, you get a positron?
Yeah, the charge conjugation, of course, by definition is a positron. But the way you describe it in quantum mechanics is that you actually have to take the complex conjugate of the equation.
Sir, I have a question.
Sorry?
আমরা যদি এখন psi আর psi star এর linear combination নেই, ওটা কি ধরনের wave কে মানে কি ধরনের wave represent করবে?
Yeah. So suppose that you have a right. So that's a very good question. So suppose you have a process in which two photons come together in a and then two photons come together and they annihilate and they create an electron and a positron. So the final state is a two-particle state, and that state will have some sort of linear, it's a two-particle state, so it'll have, it's a little bit more subtle, but it'll basically have not psi plus psi star, but it'll have something like a psi star. Okay, but your question was, what is this? So you can have states which are So this would represent an electron. This would represent, say, an anti-electron or a positron. And when you make an observation, what will happen is that psi will collapse to either psi or psi star. So, from the top of my head, I can't think of a process which will create a wave function of this form, but there may be one. But formally, it is possible. Formally, it is possible to have, if psi and psi star are both, they're both solutions, then you can have right. So what we need is that we need a physical process in which the output is either an electron or a positron. And the problem is it's very hard to do that while preserving, charge. So, charge is a conserved quantum number. And it turns out that, so suppose you have some process in which the output is, say, an electron and some other particles which has a positive charge. And or it has something like this. And so what you're going to say is that, okay, this or this, so this happens with some chance, say, I don't know, p. If this happens with some chance 1 minus p, then the thing is that this process is not described by this. It's described by something more general called a density matrix. Okay. Now, so although formally this is possible, I cannot think right now of a physical process in which this happens. But I will think about it. Okay, Nian?
Okay, sir.
Okay, any more questions?
So this wouldn't be like the mixture of an electron and a positron, right?
No, the probabilistic mixture of that is given by density matrix.
Sir, I was thinking if it was a like এরকম যে মানে টাইমের মানে দুই দিকের একটা হচ্ছে মানে পজিটিভ দিকে টাইম চাইতেছে আর একটা নেগেটিভ দিকে এরকম দুইটার মিক্সচার এর কোনো প্রসেস কিনা যেটা সাই আর সাই স্টারের লিনিয়ার কম্বিনেশন সেটা
Yeah, I mean, there are interpretations of quantum mechanics which are more exotic than the standard one. So, for example, there is an interpretation of quantum mechanics by Aronoff, of the Bohm-Aronoff effect. He has what is called a time-symmetric quantum mechanics, where you also consider wave functions of particles propagating into the past. Perhaps in that setting, there could be something like this, but I'm not sure. I actually haven't studied Yakir Aronoff's. I mean, I've attended classes, like lectures by him on this, but the details escape me. So he has papers on the time-symmetric formulation of quantum mechanics. So you can look that up, and you might find something more to your taste there. Okay, so it's a time-symmetric formulation of quantum mechanics by Yakir Aronoff. Okay. So look at that.
Yes, sir.
It's not part of the standard lore, that's for sure. Any more questions?
No, sir.
Okay. If not, I will upload another lecture very soon. Maybe tonight, if not tonight, tomorrow. I'm not my as you know, I'm dealing with some personal like my mom's health issues right now. So I'm not going to be doing a lot of the. I'm not going to be taking attendance for a few more days because, since my attendance itself is in question, I cannot expect you to always be in attendance. But it'll always help you if you attend the class. Okay, so maybe from next week I'll start the attendance. Okay.
Okay, sir.
Okay, sounds good.
Okay. Anyway, thank you very much, and have a good evening.
Okay, thank you, sir. Goodbye.